Welcome back to another video, everyone. I think we are finally done with derivatives and are ready to move on. Let's talk about the big boy of calculus, the integral. Now, a lot of the times when you think calculus, you're really thinking of integrals because this symbol, this integrand, is just so famous, right? You know, you see these memes where it's like free Wi-Fi if you can solve this integral from 0 to 3, and it's like, wow, what the heck do all these symbols mean? What could this possibly mean? So today, I am going to tell you what they mean. All an integral is just finding the area under the curve. You've probably heard that before if you've heard about integrals, where if you have a function and, you know, it looks like this, and you want the integral from, say, this is 2 to 5, right? Then the return value of that integral would be the amount of area under the curve of the function. Now, the reason why integrals are so special is because if this were a rectangle, it'd be super easy to find the area under this bit because it's just a rectangle. We know how to do that. But for any curve, how do we know exactly what the area is? Well, what if it was a rectangle? Or rather, a bajillion tiny rectangles. And so that's where the idea of an integral actually comes from. Essentially, if you have a function, maybe it looks like this, and then you want the area from here to here, well, this area is going to be the same as the sum of these two areas, which is the same as the sum of these four areas. And the idea is that as you divide it into smaller and smaller areas and you zoom in, this chunk is infinitely slim. If you zoom in all the way, maybe it'll look like this. You zoom in more, and it looks like an actual shape that you can calculate, right? It looks like a trapezoid. This is the idea of an integral, is to make it so that those rectangles approach infinity in like number, right? So they approach 0 in width. Now, let's talk about approximations for under the curve, because this is going to be very important in understanding integrals. If we have this curve and we want the value from here to here under the curve, what we can do is we can say, okay, well, maybe right here is 1, here's 2, here's 3, and here's 4. So we're looking at from 0 to 4. Well, what is it at 1? About here, right? Now let's draw a rectangle that goes over. Okay, well, what about at 2? That's about here. Now we draw a rectangle that goes over at 3. It's around here. So we draw another rectangle, and then here we draw our final rectangle. Now, to approximate the area under the curve from 0 to 4, we can sum the areas of all these rectangles, and they should be somewhat close. Let's say the actual integral is, I don't know, maybe we'll call it 3 high up here. So the integral is probably going to look somewhere around the ballpark of 4 or 5. Let's say it's 4.5. Now let's say that this has a height of 1, this has a height of 1.5, and this, maybe that one also has a height of 1.5, and then this one has a height of 3. So we have 3 from this because it's a rectangle of height 3 and width 1. So we have 3 plus 1.5 here, and then plus another 1.5 here, and then plus 1 from this final rectangle. And so we get 4.5 from these two terms. And so we get 4.5 from these two terms except there's an additional 2.5 left over, so our total value is 7. Now, that's way more than the actual value, so what gives? Why is it so off? Well, it makes sense that it's going to be more because these rectangles are obviously going to overestimate. Look at all this area that it's overestimating by. And it also makes sense for it to be incredibly off because we only have 4 rectangles. If we made this 16 rectangles, it would probably come out to like 5.1 or something like that. It would be much, much, much closer. And then as you make those rectangles approach infinity, like an infinite amount, then you get the exact area under the curve, and so it's the integral. Now let's talk about something else that is a property of integrals. They're known as an antiderivative of a function. What does that mean? Well, if you take the indefinite integral of a function f, then you get the function that will give you the area under the curve. However, if you take the integral of f prime of x, you will get f of x back, well, plus c, but that's the constant of integration. We won't talk about that quite yet, but just know that's very important. If you integrate the derivative of a function, you get the original function. Why? Well, to think about this, let's talk about a function of a derivative. Let's say you're filling water in a bucket, right? And the hose is going to turn on, it's going to get faster until it's at full, and then you're going to turn it back down. And so that's what that's going to look like. This will be amount of water flowing into the bucket per second. Now, amount per second is a rate, and so we can describe it as a derivative. So this derivative function must have some original function. But how would we find that? Well, we need to take the antiderivative, or the integral. So let's say this happens over a course of 3 seconds, and at its peak, this is also 3. Okay, well, we're assuming that this is just a triangle for educational purposes, which means that our value for area would be 4.5. Now, does this make sense for the total amount of water in the bucket? Well, let's think about it. When we multiply time by the growth is maybe it's in liters per second. And when we multiply by this bottom bit, the base of the triangle, we're actually multiplying by time, which is we'll measure it in seconds. So we have liters per second as the y value, and then seconds as the x value. So when you multiply them together, what you get is just liters. Now, what this means is liters would be the original position function, or the amount function, right? That describes the amount of liters, maybe this is per second, of the bucket. So it starts at 0. So as the hose turns on, you get a bunch, and then as the hose turns off, you start not getting as much. The rate decreases. But the final point here will be at y equals that 4.5 value that we got earlier. Now, we can do this for, instead of just a real world example, with a more vague, abstract function example. What I'm going to do is I'm going to graph dy dx. So the value of dy dx is going to be on this axis. Now, what should our x-axis be? Well, our x-axis is always x, right? That makes sense. Except this time I want to make it something a little different. I want to make it dx. Now, what this means is that every time we move over dx, we go up dy. So this bottom axis is in terms of dx, and this top axis is in terms of dy dx. Now, if we take the area under the curve, since we're finding the area of a two-dimensional shape, we'll be multiplying one dimension by another. In other words, we're going to be multiplying dy dx by dx. And those dx's have to be the same So we get dy when we integrate, when we find the area under the curve, because we're multiplying by dy dx and dx. But what's dy? It's the difference in y, which means it's just y, which is the original function. And when dy dx is the rate of change of the function, but the original function is y. So I hope all that made sense. In the coming videos, I'll be diving much, much deeper into integrals, their rules and their properties, as well as more into their conceptual and the understanding side of it. Thank you so much for watching, and I hope to see you in the next video.